Okay, I'm going to talk about excess reactant. Now, excess reactant is really exactly what it sounds like. It's the reactant that is in excess, and so there's extra of it left over. That's as opposed to what we would call the limiting reactant. The limiting reactant is the thing that limits how much product you get because it is the reactant that runs out first. And so at the end of the reaction, if there was a limiting reactant and an excess reactant, what you would have at the end of the reaction is you would have your product and then you would have some of the excess reactant remaining. Okay. On the other hand, you could have a reaction that you perform with stoichiometric amounts of things, meaning you have exactly enough of each reactant. In that case, you would run out of everything, and so there wouldn't be an excess reactant, there wouldn't be a limiting. So you would just have product in the end. But we're going to focus on looking at some examples where there is an excess reactant, and we're going to look at how you would quantify how much of that remains. Okay. Now, the picture that I have here, it does show a representation of a reaction between hydrogen and chlorine forming HCl. And what you see here, if you actually count up the individual hydrogen atoms and the individual chlorine atoms, if you were to break apart those molecules that you started with and then connect the individual atoms, you would see you get what's shown in this diagram. You would end up getting, what, 8 HCl's from those 6 H2s and 4 Cl2s, but you would still have 2 remaining H2 molecules, okay? And so that's the excess reactant, the H2, meaning the Cl2 in this case is the limiting reactant, okay? And so we're going to look at some examples with actual numbers instead of, looking at diagrams of these things and having to count individual atoms, because you wouldn't, individual molecules, you wouldn't normally do that, right? We would be measuring masses of things and doing stoichiometry to quantify, the amount of this stuff that's produced and how much is left over, figuring out limiting reactant, all of that stuff we do using mass measurements or even quantifications of moles of things, and utilizing then stoichiometry with a balanced chemical equation. So let's first do an example that tells us oxygen gas is found to be the limiting reactant when 3.75 moles of tetraphosphorus hexoxide reacts with 7.25 moles of oxygen gas. We want to know how much of the excess reactant remains after the reaction is complete. So remember, at the beginning of the question, it says oxygen gas is the limiting reactant. And so we're told that there are 7.25 moles of oxygen gas, right? And that is the limiting reactant, so I'll just write LR, okay, to indicate limiting reactant. And then we have, we have 3.75 moles of P4O6, so that must be the excess reactant. If the O2 is the limiting reactant, the P4O6 has to be the thing in excess. Now I want to know how much of the excess reactant remains after the reaction. So it's helpful to kind of ask yourself a question that isn't asked here. Well, how much of the excess reactant actually reacts, okay? Or how much is needed to react that O2? So what we're going to do is we're going to start with the substance that we know fully reacts, the limiting reactant, which is the same thing we would start with if we were trying to calculate theoretical yield. The difference here is going to be, instead of trying to calculate how much product to figure out theoretical yield, we're going to calculate how much of the reactant is used. So we're going to convert the moles of O2 to moles of P4O6, okay? So we do that by taking the numbers, the stoichiometric coefficients from the balanced chemical equation. So 1 with P4O6, 2 with oxygen. And so that tells us that we have 3.67 moles of P4O6. And that's what is needed, right? That's what's needed to react the O2, okay? And so that's what's going to react as long as our reaction goes to completion, right? And so if that's what we need, and we have 3.75 moles to start with, then what's left over is the difference, okay? So we would take the 3.75 moles of P4O6, and we would subtract the 3.67 moles of P4O6, because that is what we have to start with, and we're going to subtract what we need or what we end up using, and that's going to tell us what remains, okay? And so 3.75 minus 3.67, which I'm not really sure why I even typed that in the calculator, but that's okay. 0.08 moles of P4O6 remain. So that's how much is in excess. Okay. Okay. Now, let's look at one that's a little more difficult. So instead of working in moles, let's look at one that's in units that we would typically work with in grams. Okay. Now this one says iron 2 oxide is found to be the limiting reactant when 10.3 grams of iron 2 oxide and 5.73 grams of aluminum metal react. And then I want to know how much excess reactant remains after the complete reaction. So again, I'm just going to list the information we have. We know that we have 10.3 grams of iron 2 oxide, 5.73 grams of aluminum to start with, and we say that the iron 2 oxide is found to be the limiting reactant. So this is the limiting reactant. You're told that. Now, if you weren't told that, you should be able to determine that by doing some calculations, okay? And then that means the aluminum must be your excess reactant, right? It's got to be in excess if the other one runs out. So what I need to figure out is how much of that 5.73 is left over. And how I determine that is by first calculating how much of that 5.73 reacts. And that depends on the limiting reactant. So I would take the limiting reactant, the 10.3 grams of FeO, and from that I would calculate how much aluminum is needed. Okay, so I'd convert the grams to moles first because we have to be in moles to use the balanced chemical equation. And then I would convert the moles of FeO to moles of what I'm looking for, which is the aluminum. And then I would convert the moles to grams because I have the other value in grams. So they need to be the same unit. Okay, so I'm going to fill in my numbers. The first ratio is a molar mass, and so FeO, if I take 55.85 plus 16.00, I get 71.85 grams per mole. And then the mole ratio I get from the balanced chemical equation, so I have a 3 with the FeO and a 2 with the aluminum. And then the molar mass of aluminum is 26.98 grams per mole. So let's see, 10.3 divided by 71.85 times 2 divided by 3 times 26.98. That gives me 2.58 grams of aluminum. And so that's what we need. Or if you want to think of it, that's what's going to react, okay? Okay, that's what we need to react completely, the limiting reactant. So I take what I actually have, 5.73 grams, and I'm going to subtract what's going to react, the 2.58 grams, And that's going to tell me how much is left over. So 5.73 minus 2.58. And that tells me that 3.15 grams of aluminum is going to be left over at the end. Okay, so we'll do one more example. So this one says, what is the excess reactant when 17.5 grams of liquid pentane, which is that C5H12 there in that reaction, reacts with 17.5 grams of oxygen gas? And then I say how much of this reactant remains after the complete reaction. Okay. So the difference on this one is you're not told what the limiting reactant is, so you can't just know right away what the excess reactant is. Okay, so first you have to determine the excess reactant and then how much. Or in reality, you can kind of do that all at once when you do your limiting reactant analysis. Okay, if you do it in terms of reactants, which is what we'll do. So we know that we have 17.5 grams of each of these reactants to start with, okay? So what I'm going to do is just pick one, okay, and calculate how much of the other one is needed, okay? And if you get lucky, you end up only having to do kind of one stoichiometry calculation. If you don't, you have to do two, and that's okay. So I'm just going to pick the pentane, and I'm going to take that pentane, 17.5 grams of C5H12, and I'm going to say, if that reacts completely, how much oxygen gas do I need? Meaning I'm going to convert the pentane to oxygen. So to do that, I need to get rid of grams of pentane, and I need to go to moles of pentane. And then I can convert from moles pentane to moles of the oxygen. And then from moles, I'm going to go to grams. And so I've got my setup to do my stoichiometry converting grams of pentane to grams of oxygen. I need to fill in the numbers. So the first ratio is a molar mass. And so 5 times 12.01 for carbon. And then add 12 times 1.01. And so that gives me a molar mass of 72.17 grams per 1 mole. And then the mole ratio I get from the balanced reaction, so 8 for O2 and 1 for C5H12. And then the molar mass of oxygen is 32.00 grams per mole. So that cancels the grams of pentane, the moles of pentane, and the moles of oxygen. And that's going to tell me how much oxygen is needed. So 17.5 divided by 72.17 times 8 times 32. So that tells me that I need 62.07, or well, I guess I'll do this and round it to the right sig fig, 62.1 grams of O2. This is what I need, and I have 17.5 grams, okay? So that tells me that I actually run out of oxygen first, okay? So I need more than I actually have. So the oxygen in this case is actually my limiting reactant, okay? Meaning my C5H12 is my excess reactant. So unfortunately, I did this to where it's going to be the long way. I'm going to have to do the other calculation. So I need to figure out when that 17.5 grams of oxygen reacts, how much of the pentane is actually going to react. So I'm going to kind of reverse this calculation and start with the oxygen that I have. So I need to convert the grams of oxygen to moles of oxygen. And that's 32.00 grams in 1 mole. And then I need to convert my moles of oxygen to moles of C5H12. And that would be 1 to 8. And I need to convert my moles of C5H12 to grams of C5H12. Okay, and that is 72.17 grams per mole. Okay, so all that information was already in the previous calculation. It was just done in the reverse fraction. Okay, so I'm going to take 17.5 and divide by 32 and divide by 8 and then multiply by 72.17. So that tells me that I need 4.93 grams of C5H12. Okay, so this is what I need. And up here, these are what I have. Okay, so I have that and I need those values. So I have more C5H12 than I need, so that is definitely the excess reactant. And how much excess? Well, I subtract those. So I take the 17.5 grams of C5H12 and I subtract the 4.93 grams of C5H12. And that's going to tell me, oops, here we go, how much remains at the end. And with my subtraction, I should just end with one decimal place, so 12.6 grams of C5H12 is how much excess I remain with. Okay,